It's the physics video lecture, psci 168, video lecture 27. So we're talking about heat transfer mechanisms. I'm going to do a review of all of them and say a little bit more. And then we'll move on into some more thermodynamics, thermal physics. We have a bit of a ways to go until we get to heat engines. That's our big goal, but a couple more topics. So first of all, the heat transfer mechanisms. And now we have become familiar there are three and only three. And the first one is conduction. That's heat transfer by molecular collisions. The second one, and that's when you put your hand on something hot, you just put your hand on something, you feel the heat. That's direct heat transfer by conduction. The second one is convection. And that's heat transfer by a fluid flow. And you know, if you were to, it's a hot day outside and you open the window and a warm breeze comes through, that would be a heat transfer by convection. And the third one is electromagnetic radiation. So I'll write electromagnetic in parentheses, radiation. Okay. So this is the one we had talked about last. I want to say a few more things about that heat map. So recall we had the creek fire heat map, which I asked us to go, we'll go look at it and get some screen captures. There are other sources like that, but this was an interesting one, and I want to say a little bit about how this is done, because you can go onto that page in the middle of the night and there will be updates every so and so many hours, because there's thermal radiation. So namely this electromagnetic radiation. So let's draw a picture of our Earth. Okay. And then we have a satellite orbiting. And some of the, okay, so let's say we've got a satellite orbit. It's going to be a fairly near the Earth one. So there's our satellite, and it has a little, depending on how big the satellite is, it definitely has a dish that is facing the Earth. So there's a little satellite dish. Just like you have a satellite dish at home, perhaps, that happens to be aimed at a satellite. The satellite has a dish that's aimed at the Earth, and it is picking up thermal radiation from the fire. Okay. So that's why it works at night. The thermal radiation is not the visible wavelength, it's a longer wavelength, but the detectors can pick it up. So they pick up radiation, and they have sensitive enough detectors to tell what the wavelength is and what the intensity is, and so they actually are able to, for a given location, estimate the thermal output in megawatts. And I was looking at that some more. Thermal output from some substantial fraction of 1 megawatt up to 100 megawatts on some of the more intense fire dots, so to speak. So yeah, let's put a couple of words there for that. So we have satellite, which we've studied, so we know how fast and how high and so forth. So we have satellite detection of infrared radiation. And you perhaps want to revisit that page and have a look at that again. They give some information about what the satellite is that picked up the data, and this, like I said, the size of the local fire, and you can see from day to day whether it's spreading or not. So satellite detection of infrared radiation, and it works day and night. So that was the heat transfer by radiation. That was just one example. Of course, the greatest example is the sun, which is radiating energy to us in all wavelengths, heat, visible, and so forth. Okay. Now, one application of this before we move on there are many applications, but there's one I want us to make sure we understand. How does a Dewar flask or a thermos, that's a trade name, so we often speak about a thermos bottle. It's actually a Dewar flask. How does that work? So I'm going to draw one, if I can. Okay, so this is going to be the thermos. And why do I have two walls here, inner and an outer wall? Put a cork in it, is because we have vacuum between two layers of stainless steel or glass. So inside there is a vacuum, that is to say there's nothing. Gas has all been pumped out. And if you've ever used a thermos like this, you'll notice that the only place where you feel the heat or the cold is at the cap. Okay, the rest of it seals it off pretty well. So, because there's a vacuum here, heat transfer by conduction and convection are suppressed. Okay? That's why this thing keeps hot things hot, keeps cold things cold. So heat transfer by conduction and convection are suppressed. And how about radiation? By silvering the glass here, so you'll notice it'll be silvered on both sides of the glass flask. So it's silvered, and that reflects the radiation, to reflect radiation. So if you look inside, you'll notice the inside is silvered, and if you have something hot in there, you want the radiation that would radiate out to be reflected back inside. Okay? So the reflection is important. So the thermos or the Dewar flask suppresses all three of these heat transfer mechanisms, and that's why if you put something hot in there, it stays hot. Put something cold in there, it stays cold. So yeah, suppose you put something hot inside, just relatively hot, okay? Then it's in contact with the walls, but it's a very thin glass wall. There's heat transfer there, but it's stopped at this vacuum layer. Okay? The heat transfer, because you have no molecular collisions, you have no convection. Anything at all is always radiating electromagnetic radiation. And that is being reflected back in because it's silvered. So just understanding how a thermos works, you've got all three of these heat transfer mechanisms functioning. Okay, good. So again, we can find many, many more applications. These are just the basics. Yeah, a couple more. Another example. Insulation in the walls of a house. Okay, so let's just take the wall of a house, and there's the wall, and just for the sake of argument, inside, outside. Okay, here's the inside of the house, here's the outside, here's the wall. So you want to suppress heat transfer through the wall because maybe it's cold outside, you want to keep the heat inside. Or it's hot outside, you want to keep the heat outside. But in either case, you want to suppress the transfer of heat across the wall. So how do you suppress conduction? Okay. If you just had an empty airspace, that would suppress conduction because air conducts much less than any solid, okay? So you can have an empty airspace, but you're not going to suppress convection. And in fact, let's let it be hot inside and cold outside, okay? T, H, T, C, it's winter time, coming up soon enough. You want to keep the heat in the house, okay? So how do you suppress the transfer of heat from inside to outside? Again, if you just had air here, you'd say, well, that's a fine insulating layer, except the air will form convection currents. And those convection currents will actually be kind of the circular type of thing here, and they will carry heat from the inside to the outside. So what is done is we stuff insulation into the wall, fiberglass insulation. It has very low conductivity and it suppresses the convection. So we would have here inside the wall, fiberglass insulation. Okay, it's fluffy, so it's loosely packed. It suppresses conduction. It suppresses convection because the air currents cannot form because there's no adequate space for the air currents to form. And what you'll notice if you ever look at a construction site, the fiberglass insulation has foil covering on both sides, and that foil on the fiberglass insulation is suppressing the radiation. Even though that stuff is locked away in the wall where it's dark, okay, it's still suppressing heat transfer by radiation. So I'm going to write here fiberglass insulation with foil, probably it's aluminum, foil coating. Or is it? I'll just write aluminum foil layer. It's the outside layer, aluminum foil. So yeah, you'd have, you know, this insulation here where it's fluffy fiberglass, and then you'll have aluminum foil, which we'll call blue, on the outside. And again, that product, that stuff suppresses heat transfer, all three mechanisms. Okay, so let's leave it at that in terms of the heat transfer. It goes on and on. It's a fantastic topic, but we must move on. Okay, so there's one more major thermal physics topics before we get to the engines and the work, which is where we're headed. And this concerns the energy involved in phase transitions. So we have to talk about phase transitions and energy. So what is a phase transition? We're talking about the phases of matter. So the phases of matter, solid, liquid, gas. And there's a fourth phase referred to as a plasma. So let's just take a piece of ice, for instance, solid, water, ice, that's a solid. You melt it, it's a liquid. You boil it and vaporize it, it turns into a gas. But that's not the end of it. If you can actually pull apart the molecules, so water is H2O, You can separate it to hydrogen and oxygen, and then if you can separate the hydrogen to protons and electrons, okay, pull those apart, then you're at the point where you have a plasma. So you've separated into its elementary constituents. Each of these stages here are an energy progression. And we're just going to concentrate on the first three. You know, so if we had a picture, we could say we've got ice, so that's a solid. We'll draw a cube. That is an ice cube. And we're going to add some energy to it. And it's eventually going to turn into water. So now we've got a beaker full of water. And if we add some more energy to it, that is to say, we heat it up even more, we can vaporize it. And I'll just draw a balloon with gas in it. Okay, so there's our solid, liquid, gas. And we add energy. And this is our day-to-day experience. Okay, we have some ice, we can see it melt, and we know that if we put it in a, put it in a skillet on the stove and really heat it up, definitely more or less rapidly turn it into water. And if we boil it away, it'll all be gone and it will have vaporized. And so each of those stages requires energy. What we don't necessarily consider is the fact that now that we're physicists, we know energy is conserved. We could actually go from a gas back to a liquid, and then we would have to return, that energy would be returned. And if we go from a liquid to a solid, that, in other words, the energy arrows should be reversed. Okay, so we're gonna talk about that as well. Let me go ahead and write that here. So up here, energy is absorbed, and down here, energy would be released. So absorb energy, that's down here, and then in this direction we'll release energy. But I have to make this a bit more quantitative now. Absorb energy, go from solid to liquid to gas, and you go from gas to liquid to solid, you're releasing energy. Okay, now we're going to make this a bit more quantitative. So what we're now going to consider is the energy required to produce these changes. And I'm going to make a pretty large graph. This is a graph you'll find everywhere, good to understand. So we can title this graph Energy Required to Melt or to Heat Water. Let's see, what's a good title for this graph? It's going to be a pretty big one. Okay. So on this axis, we're going to have temperature in degrees Celsius. And on this axis, we've got to leave a little room to the left and underneath. So on this axis here, we're going to have Q in joules. So that's energy. So that's temperature versus added energy. For water. This graph could be done for many substances, but we're going to do it for water. Because we know some specific interesting temperatures here. So 0 and 100, those are pretty relevant for water. Melting, boiling. So let's start with water at, say, 20, 40, 60, 80, 100. We'll just start at water at minus 20 degrees. Okay, so we've got minus 20, and we have some water, and we're going to add energy, and the water is going to heat up. Okay. So that's that line right there, and we say Q equals M, specific heat of ice, delta T. That refers to how much water, what the temperature change is. So for example, if we went from minus 20 to 0, then delta T would just be 20. Okay. Minus 20 to 0, delta T would be 20. Okay, now here's what's interesting. So we're adding energy to ice, starts at minus 20. Now if we do it slowly enough, we have an ice cube all the way up to 0 degrees. Then what happens? What happens is that the ice melts without the temperature changing. So you do this very slowly and carefully. This is the melting, but the temperature is staying constant. That's why we have to build this graph and not just talk about it like that. Okay. It's melting, and when all of the ice has melted, you then have water. So here you had ice at 0 degrees, now you have water at 0 degrees. And this amount of energy here, Q is equal to mass times latent heat of fusion. So L sub F is called the latent heat of fusion. Let's go ahead and write that over here. L sub F equals latent heat of fusion. This is really interesting because this is an enormous amount of energy that it takes just to melt ice to water without changing the temperature. And so the units, since this is joules and this is kilograms, it's joules per kilogram. So L sub F has the units joules per kilogram. And L sub F for water, you can look this up. In fact, you can get a whole table of latent heats of fusion. For water, it is 3.33 times 10 to the 5 joules per kilogram. And first of all, that's just a number, but we're going to put it into context. Okay. So latent heat of fusion. And you could find the latent heats of fusion for several substances and make a little, print them out or fill them into your notes again. So homework, find L sub F for, we have it for water. What else could we have it for? Find some substances that interest you. Anything that's water-based, it's going to be about the same, but anything that can melt will have a latent heat of fusion. So you could find latent heat of fusion for some metals. Okay. For, say, lead, iron. How about that? A couple latent heats of fusion. Glass, other things as well, okay? Things that can melt. But we're talking about water now, okay? So now the water, the ice was warmed up, it has melted, and now, of course, it's going to heat up, and we're going to gradually heat it up to 100 degrees Celsius. I'm just going to draw another straight line. And that's going to take a certain amount of energy as well. Now, we know this one also. The energy required is MC delta T. This was C sub ice. This here is C sub water. Okay, you have that in your notes. Specific heat of water is about twice as much as specific heat of ice. So specific heat of liquid water. Okay. And delta T is 100 degrees. So depending on the mass, that's how much energy in joules it took. And notice it was just increasing. The water was increasing in temperature. Now what happens when we get to this temperature here and keep applying heat, we get what's called vaporization. And vaporization was what I was talking about up there, right? When we turn the water from a liquid into a gas. So we've got the vaporization, and again, if it's done carefully, slowly, we're adding energy, but the temperature is not changing. That's what's so important about these horizontal lines. Temperature's not changing, and we have Q is equal to the mass times the latent heat of vaporization. So I had the latent heat of fusion. I'm going to erase this now. We're going to have the latent heat of vaporization. And so L sub V, latent heat of vaporization, and again, the units, just divide by mass, you can see you have joules per kilogram. So if you print out some latent heats of vaporization or you add them to your notes, then you want to look them up with proper units. They have to be joules per kilogram. Same as the other ones. Those are the units we're using, right? Joules per kilogram. So latent heat of vaporization, and L sub V for water is 2.26 times 10 to the 6 joules per kilogram. So that's another power of 10. That's a lot, okay, to vaporize all of that water. Now, since these were just numbers, I want to make an important number comparison. I want to compare the amount of energy it takes to melt the ice to the amount of energy it takes to heat it up from 0 degrees to boiling temperature, which is 100 degrees. Okay, we want to compare those amounts so we can put them into perspective. See how we're doing time-wise here. We've got nothing but time. Good. Okay, let's go ahead and erase this. So the two amounts of energy, how much it takes to melt ice and how much it takes to bring that water up to boiling. So Q sub melt ice divided by Q sub heat water from 0 degrees Celsius to 100 degrees Celsius. Those are the two amounts of heat that we're comparing. Now this one is 3.33 times 10 to the 5 joules per kilogram. And this one here is 4,186 joules per kilogram degrees Celsius times 100 degrees Celsius. I should have put the formula here first. I'll put it after. Okay. Those are the numbers. So that's 3.33 times 10 to the 5 divided by 4.186 times 10 to the 3, 4, 5. So that is 3.33 divided by 4 point, I'll round 2. You'll notice all the units cancel, so that's approximately 3/4. 0.75, 75%. So that is a pretty unintuitive amount. Fully 3/4 amount of the energy that it takes to boil a certain amount of water is what it takes to melt the same amount of ice. Okay, 3/4 of the energy. I think everybody knows, a washed pot never boils. It takes a lot of energy to boil some water. And you know, we're getting it out of the faucet at room temperature, taking it from 0 to 100 degrees. Yeah, this formula, by the way, Q melt over Q sub heat, which I'm just going to call it, this was M L sub F divided by MC delta T, and we plugged in delta T equals 100 degrees, okay? So that's where that came from. So that's a lot of energy. Now, one interesting thing about it is that, remember my prior graph, I said we can release that energy. I'm going to draw that picture again. I'll draw it right here just to remind us. So we've got the ice, we add heat to it, we've got the beaker of water, we add heat, and we have the balloon full of gas, okay? And then I said we could release that energy, and release that energy to go from gas to fluid to solid. So what that means is this many joules per kilogram to melt ice to water are released when water is frozen to ice. Okay? Completely unintuitive that when the water freezes, it releases that enormous amount of energy. So the important note for this whole thing here that you want to, these were just numbers, but this is the whole point of this. Freezing water releases energy. Okay. Freezing water, or anything that's solidifying, releases energy, thermal energy. It's so much you're wondering why you can't just stand in front of a puddle of freezing water and warm your hands, but you can't do that. But I'll explain that in a moment. But yeah, this is the very important takeaway, and it has some really profound applications, which I will draw up here. In a sufficiently large picture. I'm talking about just reversing this part of the curve. So if you added energy to melt it, and you're going to obtain energy, it's going to release energy when you freeze something. So let's go ahead and open up a little bit here. Okay, and the application, and this is one you guys should look for some images for. I've actually never looked for images of flooding the orchards in the winter. So, application, flooding the citrus orchards. They do this here in the Central Valley, flooding the citrus orchards to avert damage to the crop, okay? To avert damage, freezing damage to the crop. I've actually seen this, I didn't take a picture of it, but what happens is if there's a really cold forecast, cold air coming in to a citrus orchard, they'll actually flood the floor of the orchard with water, and that somehow helps avert damage, freezing damage. So let me explain that. So let's draw a tree. Okay, so we've got a tree here with a bunch of fruit on it. Okay, that's a tree. This is the ground. And we're going to have water that we want to freeze. And the question is, how can that avert damage to these crops? So what's coming in here, though, is cold air. Say coming out of the mountains So cold air sweeps through here. And let's give it some temperatures now. So T is equal to, say, let's have a hard freeze coming through -4 degrees Celsius. Pretty cold, okay. Maybe enough to freeze a crop. I'm just making up numbers, okay? How cold is the water? Piece of water, as it freezes to ice, is equal to 0 degrees Celsius. Okay, what's colder? 0 or -4? Okay. 0 is TH and -4 is TC in our prior graphs here. Remember, we always have heat flowing from TH to TC. Right, that's our famous cartoon. So what we're getting when the temperature of the air is -4 degrees and the water is 0, we're actually giving off radiation, thermal heat transfer, all three forms as far as we're concerned here. So it's being given off at a low temperature, but the point is that energy can warm that air maybe from -4 to -1, and -1 maybe not cold enough to damage the crop. So this flooding the citrus orchards, see if you can get some images of that. I've actually seen them. I've driven through the countryside here in the winter, very clear day. There's all this ice on the ground in the orchards. Okay, if you see that, then you know what was going on. So let's put this as a homework as well. So here, I'll put this in black. And by the way, what's going on, just once again, the energy is being released from the liquid state as it goes from the liquid state to the solid state. All that energy is being released. Good, so let's call that a homework as well. Homework images. So if you can get some images of that, that'll be a great addition to your notebook. Images of this, and the other thing we wanted, some numbers for those latent heats. And that will be our discussion of heat. Well, we did the heat transfer mechanisms. That's our discussion of the states of matter and energy. So, you know, there are subtleties to it. We knew that we have to add heat to melt ice and to produce steam, but there's a lot of energy involved in these heat transfers. You know, you may find a good version of this graph as well. You can print out one or two of these. It's very stereotypical, so you'll see it. Okay, change the state, latent heats of fusion, latent heats of vaporization. Okay, I think that's going to be it. Let's see how we're doing here. Okay, that's perfect. So next time we'll be ready to possibly revisit this briefly, but then we'll start talking about the heat engines. Okay, until then, yeah, try to get some of these images, and we'll see you next time.